Hi, Assalamualaikum and good day. Today we will continue with feed forward and ratio control. So we will discuss on these few subtopic. The first one regarding the feed forward control, just an introduction, and then ratio control and other control strategies. Right, before we proceed with feed-forward control, let's recap on what is feedback control. Right, okay, as you know, feedback control is one of the simplest process control scheme. And feedback control will measure a process variable and then sends the measurement to a controller for a comparison with set point. If the process variable is not at set point, control action is taken to return the process variable to set point. So the advantage of feedback control is that corrective action occurs as soon as the control variable deviates from the set point, which means that there is no corrective action is taken until after there is a deviation in the control variable. But then, what is the disadvantage of feedback control? Okay, one of the disadvantage of feedback control is that it does not provide a predictive control action to compensate for the effects of known or measured disturbance. So if you want to measure a disturbance, what can you do is you add a feed-forward control. So feed-forward control will measure the disturbance and then try to proactively adjust the final control element in order to anticipate or to predict the effect of the disturbance before it creates a deviation from the set point. Alright, now okay, let's take a look at this diagram. Okay, can you tell me what is the type of control used here? Is this a feedback or feed-forward control? As you can see, this is a boiler drum, and then the control objective here is to control the liquid level in a boiler drum, meaning that you want to control the water level in this boiler drum. So your control variable is what? Is the level of water in the boiler drum. And then what is the manipulated variable? The manipulated variable is the flow rate of water or flow rate of feed water. Flow rate of water being fed into the boiler drum. So this is a feedback control. Right. Now, can you tell me what is the disturbance variable? The disturbance variable in this case is the what? The steam flow rate. Okay, this control tend to be quite sensitive to rapid change in the disturbance variable, which is the steam flow rate as a result of the small liquid capacity of the boiler drum. Okay, besides the rapid disturbance change produced by the steam demand here made by the downstream processing unit. Okay, now maybe this steam in the downstream processing unit, you have a reactor here that require your steam, right? So this will disturb the controller here. This will disturb the feedback controller of liquid here. So now what can you do? What you can do is you can add a feed forward control so that it can predict the effect of the steam flow rate before it disturbs the process. So this is how we add the feed forward control, where we measure the disturbance first and then we put the controller feed forward control and then connected to the a final control element. So this is an example of feed-forward control, right? So the basic concept of feed-forward control is to measure the important disturbance variable and take a corrective action before they upset the process or before they disturb the process. Okay, the feed-forward control is usually or normally used in combination with feedback controller. So you know this is your feedback controller, and then you add another controller, which is the feed-forward controller. So this is a feedback plus feed-forward control. And then you have the controller with a summing function here, where it is used to sum up the input from both feed-forward loop and the feedback loop, and then send a unified signal to the final control element here. Okay, ratio control. What is ratio control? Okay, ratio control is a special types of feed-forward control where the objective of ratio control is to maintain the ratio of two process variable at a specified value. Okay, these two variables are usually your manipulated variable and your disturbance variable. Okay, in ratio control, the ratio is controlled rather than the individual variable, where the ratio is expressed as the manipulated variable divided by the disturbance variable. So this is how you construct or you draw the ratio control loop, where you need to measure both disturbance and the manipulated variable. So which one is the disturbance and which one is the manipulated variable? So this is your disturbance variable and this is your manipulated variable, because you have your final control element here, which is the control valve, right? So as you can see, you need to measure both. So for disturbance, you connect the transmitter to the feed forward controller and then connect it to the feedback controller, and then connected to the final control element. And note that the feedback controller here is also connected to the transmitter, flow transmitter that measure your manipulated variable. Alright, this is another example of ratio control where you want to control the ratio of acid and water that fed into this tank. Alright, so can you tell me what is the manipulated variable and what is the disturbance variable? Right, as you can see, you have the final control element here, meaning that this is your manipulated variable. So your manipulated variable is the flow rate of acid, and then the disturbance variable is the flow rate of water. Why? Because as you can see here, you have your feed forward controller. Because as I mentioned earlier, okay, feed forward controller will measure the disturbance variable. Right, so the feed forward controller will be connected to the feedback controller, and then will be connected to the final control element to execute or to do the corrective action or to adjust the ratio of acid and water. And then your R in this case will be equal to flow rate of acid flow rate over the water flow rate. Because why? Because your R is equal to manipulated variable divided by the disturbance variable as mentioned in the previous slide. Typical application of ratio control include setting the relative amount of component in blending operation. So you have your blending system. So you have few components that you want to blend. So maybe you want to control at a certain ratio or certain amount. Then you use a ratio control. And then you can also use a ratio control to maintain the stoichiometric ratio of reactant to a reactive. So for example, you have a reaction inside uh, a stirred tank reactor. So this, for example, this is the reaction. So now you want to control the stoichiometric ratio of your reactant. So your reactant are A and B. So you want to maintain this stoichiometric ratio. So 1A and 2B. So you use the ratio control to do this. And then you might also want to keep a specified reflux ratio in distillation column. So you use a ratio control, and then you can also need the ratio control in a furnace to maintain the fuel and air ratio. Okay, a ratio control can be implemented using two methods. So this is the first method, where we measure both the disturbance stream and the manipulated stream. Right, and then the measured ratio Rm, which is equal to measured manipulated variable over the measured disturbance variable. Okay, the output will be sent to the ratio controller that will compare the calculate or the uh, measured ratio with the desired ratio, and then the controller will adjust the manipulated variable accordingly. Okay, one advantage of this method is that the measured ratio is calculated, so the RM is calculated, but it has a disadvantage where a divider element must be included in the loop, and this element will make the process gain vary in a non-linear fashion. Because Kp, this is your gain, so gain will be equal to the change of the ratio over the change of the manipulated variable, which is also the inverse of the disturbance variable. So in order to overcome this disadvantage, another method number 2 will be used. Okay, in method 2, the flow rate of the disturbance stream will be measured using the flow transmitter and then transmitted to the ratio station, which multiply this signal by an adjustable gain whose value is the desired ratio multiplied by the span of both dV and mV. Now, the output signal, okay, from the ratio station is then used as the set point for the flow controller here, which then will adjust the flow rate of the manipulated stream U. Okay, the advantage of method 2 is that the process gain remain constant. For example 15.1, okay, this example use a ratio control scheme to maintain a stoichiometric ratio of two reactants, which are hydrogen and nitrogen, in an ammonia synthesis reactor. Okay, so for this example, please try it by yourself. All the solutions are provided. Okay. This is a block diagram of feed-forward plus feedback control system. So as you can see, this is the feedback part that we have learned previously, and then this is the feed-forward part. Okay, so you have your disturbance, and then you have your transfer function for your disturbance, and then connected to the transmitter in order to measure the disturbance variable. So for feed forward, you need to measure the disturbance variable. Okay, so now the transmitter is connected to the feed forward controller. So you have your transfer function of your feed forward controller as well, and then you have the summing function here to sum up the controller action of feedback and feed forward. Right, once we have our block diagram, we can now derive the closed loop transfer function for disturbance change, meaning that we want to have an expression of y over d, the change of output over the change of disturbance variable. Okay, so y over d is what is a regulator problem, right? So in regulator problem, we assume that your set point will be equal to 0. So you need to derive using the algebra relation that we have learned in the previous chapter. For example, here, you know y is equal to yd plus yu. And then what is yd? yd equal to gd d. And then what is yu? yu is equal to GPU. And then what is U? You need to derive one by one until you have an expression of Y over D. Okay, so you want to have this final expression. So for feedforward plus feedback control system, so this is the closed loop transfer function for the disturbance change given in equation 15.21. Okay, so now ideally we want to have a perfect control. What is perfect control? Perfect control means we want our control variable remain exactly at the set point with any change in disturbance variable, meaning that you want your what control variable is what is y lah. So you want y equal to y set point. So if y set point equal to 0, meaning that your y is equal to 0. So now this can be done by set the numerator equal to 0 because the numerator here is your y, right? So you set the gd plus the numerator, gd plus gt, gf, gv, and gp equal to 0. Now rearranging this equation to get the expression of GF, so you finally will get this expression for GF, or the transfer function for feed forward controller. Okay, now let's analyze the stability of the closed loop system in figure 15.11. So this is the block diagram of a feed forward plus feedback controller. So let's analyze the stability. So as you have learned previously, the stability can be analyzed using what? Using the characteristic equation. Alright, from the closed-loop transfer function in equation 15.21, this is the one that we have discussed earlier, we know that the characteristic equation is the denominator part, right? Okay, so this is your characteristic equation. Okay, looking at the characteristic equation, if you notice, there is no GF term, right? The transfer function of the feed-forward controller, meaning that the feed-forward controller has no effect on the stability of the control system. So this allow the feedback and feed-forward controllers to be tuned individually. Alright, this is the typical configuration of feedback plus feed-forward control system. So as you can see here, you have the feedback controller, feedback element, and then you also have the feed-forward element here. and then you have the summing function here to sum up the controller output from both feed-forward controller and the feedback controller, and then it will send the corrective action to the final control element. So as you can see here, this is a boiler drum, so the control objective here is to control the level. So the level is our control variable, level of water in the boiler drum, and then the MV here is the flow rate of feed water, and then the disturbance variable here is the one that we have measured, is equal to the steam flow rate. So with this configuration, based on the previous closed loop transfer function, we have analyzed the denominator part, and at the denominator part, there is no transfer function of feed-forward controller, meaning that the feed-forward control does not affect the stability of feedback control loop. Alright, alternatively, we can have another configuration of feedback plus feed-forward controller where we don't have any summing function over here. So as previously, we know that we have the summing function over here to sum up the controller output of feedback and feed-forward controller. But in here, there is no summing function. And what happened here is that the output from the feedback controller, so this is actually your AC, the composition controller, but then it is written as FB just to indicate that this is feedback controller. So now the output from the feedback controller is sent to the feed-forward controller as the new set point for feed-forward controller. So what happened is that the feed-forward controller will compare the measured value with the new set point and send the corrective action to the final control element here. So using this configuration, the feed-forward control can affect the stability of feedback control system. Why? Because the input for feed-forward controller here depends on the output of your feedback controller. That's why it will affect the stability of the feedback control system. Okay, another type of control other than feedback and feed-forward is cascade control. In Cascade Control, there are two controllers. The first one is the master or primary controller, and the secondary controller is called as slave. Okay, now in Cascade Control, the output from the primary controller, so this is the output, will be used as the set point for the secondary controller. So as you can see here, you have a process fluid being fed to the shell and tube heat exchanger for heating purpose, because you want to heat this fluid to a certain temperature. So the control objective here is to control or to maintain the temperature of this stream at certain value. So the CV here is the temperature of shell and tube heat exchanger outlet, and the MV here is what? Is the steam flow rate. Okay, cascade control is used when the disturbance is associated with your MV or manipulated variable, meaning that this is your manipulated variable. Now, your manipulated variable can also become your disturbance. So, before it disturbs the process, you will have a predictive control action using the cascade control. So this is how the cascade controller works, where you have the primary and the secondary controller to control the temperature of this stream. Alright, this is another example of cascade control in a furnace temperature control scheme. Alright, so if you can see here, you have two controllers. So the first one is the primary controller, because you want to control the temperature. So the temperature controller is your primary controller, and the secondary controller is the pressure controller. Because if there is a disturbance occurs in the fuel gas pressure, it will affect the fluid of fuel gas, which will disturb the furnace operation, because it disturbs the hot oil temperature. Right, so before it disturb the furnace operation, you put a secondary controller here where you measure the fuel gas pressure, and then connect it to the secondary controller, which is the pressure controller, and it will provide a predictive control action for this furnace. Right, another type of control that is commonly used is split range control. In split range control, there are two final control elements, or two control valves. The controller in the split range control will select which valve that need to be open or need to be shut according to the control objective. So now, the control objective here is you want to maintain the pH of tank 100 to be 6. Okay, if the pH here is greater than 6, so the controller will open this valve so that acid is dosed to this tank to reduce the pH to 6. But if pH is lower than 6, if this pH is lower than 6, the controller will select this valve CV102 to open so that sodium hydroxide can be dosed to this tank to increase the pH to 6. So this is how the split range control works. So I think that's all for today, and thank you for your attention.